That's right. I'm Luke. I'm going to talk about evolution and learning in differentiable robots. So I think many of us here are inspired by the forms and functions that we see in the natural world. For example, on the slide you see several different diverse and sophisticated biological machines, all of which came about through a large-scale evolution and learning process. And we applied a similar idea to robot design. These are some of the robots that we discovered. Our methodology joins morphological evolution with massive scale gradient-based learning, and we find that we're able to increase the scale of robot design search by orders of magnitude. These are some of the bodies in motion. Each of these is modeled using a mass spring system, and the bodies operate with a fully closed-loop controller, which I'll discuss in detail later. As I said, the body is evolved and the controller is learned. So let's take a look at how the algorithm works in detail. The first component is the evolution of morphology. We start by randomly sampling a population of robots, and each of these produce offspring through morphological mutation. The second component is learning. Each robot undergoes a period of learning in a massively parallel differentiable physics simulator. Zooming in, we can see that there's a neural network that controls actuation through simulation, producing behavior, and the simulator differentiates a loss function to produce gradients for improving future behavior. After learning is complete, the best robots are selected to move on, and they form the new population. Then this process is repeated 1,000 times over, evaluating around 10 million robots within a single run. Ultimately, we selected one design from simulation and we manufactured it, demonstrated an effective sim-to-real transfer, and I'll discuss this in some detail later. So returning to the mass spring system, each of these purple masses corresponds to a proprioceptive sensor that's measuring velocities and component displacements. The gray links are passive springs, the light green links are active and expanding, and the dark green are active and contracting. Like I said, this is a closed-loop system, unlike most evolved robots. So each spring in the body receives motor control signals. Each mass in the body is a proprioceptive sensor. There's a set of sinusoidal waves that serve as a central pattern generator, and these both provide input to a neural network, which then produces motor output in order to close the loop. What we found is that evolution produces what we're calling increasingly differentiable robots. So the y-axis of this plot is measuring the performance of robots in terms of their body displacement, and the x-axis is measuring evolutionary time in terms of the number of morphologies seen so far. The light green line shows the initial performance of robots with a random neural network controller, and the dark green shows optimized performance after learning. The increasing discrepancy between the initial and the optimized performance indicates that evolution is discovering body plans that are more and more amenable to gradient-based optimal control. Well, control, not necessarily optimal, but learned control. Hence the phrase increasingly differentiable robots. Now this is one body that we would say is not differentiable. The robot undergoes 35 iterations of learning. Each of these green lines corresponds to a center of mass trace, measuring how far the robot moved. And you can see from the beginning to the end, it cannot locomote very far. These next set of robots that you'll see here are increasingly good learners, but relative to the population at large, we would not say they're particularly high performers. On the bottom row, we see some very high performers. These robots all begin with very, very low behavior scores and improve dramatically through learning. We would call these robots very differentiable. Unlike most work in differentiable simulation, which has been restricted to flat terrain, we also investigate rugged environments. So here, the mass, when a mass contacts the ground, the friction force is computed dynamically. However, the simulator remains fully differentiable, allowing these robots' control policies to be optimized end-to-end with gradients that propagate through ground contact. And finally, coming back to the sim-to-real, the 2D simulated robot was extruded into a third dimension for manufacturing. We used shape memory alloy springs for the active components, and the learned actuation pattern was manually transferred to the physical machine. We found that under a fixed number of actuation cycles, the simulated and the physical robot traversed a similar distance, and that in a control experiment where we removed one spring, the physical robot this time locomoted in the opposite direction. Thanks for your time, and I'm happy to take any questions.
Any questions?
Thanks for your talk. It's quite impressive. I'm wondering, have you included self-collision into your evolution?
Sorry.
Okay. So, do you think we will have some influence on your performance?
By modeling self-collision, you mean?
Yeah.
Yeah, so we currently don't model self-collision, but it's something that we're exploring in future work.
Okay.
I suspect that it's essentially just a trade-off in computational overhead. So we're certainly working on prototyping physical systems that we can create a tighter coupling for sim-to-real transfer with. Of course, in the physical world, self-contacts are implicitly modeled. So it's definitely of interest to us, but currently we don't have that supported in this system.
Thanks for your answer. Yeah.
One more question over there.
A very cool idea, thank you. Quick question, is there any energy involved into the selection? So I mean, like an evolution, we have locomotion, which is energy efficient. Is it something you are taking care of?
In terms of the selection force?
Yes.
No, the selection is strictly in terms of the learned locomotive performance.
Thank you.
Let's thank the speaker again.